Have you ever wondered how we can know with real confidence that one thing is better or faster or just plain different from another when we only have a small piece of the puzzle? Well, today, we're going to dive right into that. We're exploring the super powerful world of statistical inference to see exactly how we compare two different groups using data.
At its heart, we're trying to answer pretty basic questions. Questions like these. Are customers in a downtown store older than the ones out in the suburbs? Is this brand new drug really a game changer compared to the old one? Or is the difference we're seeing just random luck? These are exactly the kinds of puzzles that statistics helps us solve.
And believe me, this isn't just for textbooks. Really high-stakes decisions depend on these methods every single day. Take the FDA, for example. They rely completely on comparing patient groups to figure out if a new medicine is safe and effective enough to be released. Seriously, the logic we're unpacking today literally saves lives.
So, here's our game plan for this explainer. We'll kick things off with the core question we're trying to answer. Then we'll walk through an ideal world case and then a much more realistic one. We'll even see how all this works for percentages, not just averages. And then we'll wrap it all up with the big idea that you can use just about anywhere.
Okay, first up, the core question. I like to think of this as going from blurry photos to clear answers. Imagine you're trying to understand a huge picture, but all you have is a small, kind of blurry snapshot. That's our challenge.
It's just impossible, right? You can't survey every single shopper in a city or test a new drug on every single person on the planet. So what do? We take a smaller group, we call it a sample, and we use what we learn from that little group to make a really smart, educated guess, a statistical inference about the whole population. That's the big idea right there.
All right, let's move on to our second part, the ideal case. For a minute, let's pretend we're in a perfect world, where we already know a key piece of information, how spread out or varied our populations are. Statisticians call this the standard deviation, and they use the Greek letter sigma or sigma to represent it.
Okay, let's make this real with an example. We've got two department stores, one in the inner city, one out in the burbs. What we really want to know is the difference between the true average age of all the city customers, we'll call that mu1, and all the suburban customers, or mu2. Our mission is to figure out the difference between those two.
So this is our strategy. Since we can't possibly ask every single person their age, we do the next best thing. We take a totally random sample of shoppers from each store. The difference in the average age of our two samples becomes our starting point, our best guess for the true difference across everyone.
And here's the data we actually got. From the city store, we grabbed 36 people, and their average age was 40. From the suburban store, we got 49 people, and their average was 35. So, right off the bat, our best guess is that city shoppers are about 5 years older. But can we really be sure about that number?
To figure that out, we need to create a margin of error. Now, don't let this formula freak you out. Seriously. Just think of it like a recipe. It takes our best guess, that 5-year difference, and it folds in our sample sizes and what we know about the population's natural spread to cook up something called a confidence interval.
And voila, here's our result. The math tells us our answer is 5 years, give or take about 4 years. So what does that really mean? It means we are 95% confident that the true average age difference is somewhere between about 1 year and 9 years. And here's the kicker. Since that range is entirely positive and doesn't include 0, we've got really solid evidence that there is a real difference.
Okay, that was nice and neat. That was the ideal world. But what happens when we don't know that population spread, that sigma value, from the start? Which, let's be honest, is almost always. Well, welcome to Section 3, the real world. This is where things get a lot more practical.
So here's the big change. In the real world, we almost never know sigma. We have to estimate it using our sample. Because that adds a little bit more uncertainty into the mix, we have to switch our tools. Instead of using the standard normal, or Z distribution, we use a slightly different tool that's built for this uncertainty. It's called the student's T distribution.
So for this, let's tackle a new problem. A company is wondering if some fancy new software actually helps their analysts finish projects faster. So they run an experiment. One group uses the old stuff, another group uses the new software, and they time how long it takes both groups to complete a project.
And yep, another formula. But again, please do not sweat the math. The big idea is what matters. This formula is for something called a t-test, and it's specifically designed for this real-world situation. It cleverly adjusts all our calculations to account for that extra bit of uncertainty we have because we're estimating the spread from our data.
And check out the results. The bar chart shows the group with the old tech took, on average, 325 hours, but the group with the new software, only 286 hours. Now, the t-test is what lets us answer the crucial question: is that difference big enough to be statistically significant? In other words, is this a real improvement, or could it have just been luck? In this case, the stats confirmed it. The new software is a real time saver.
So far, we've been all about averages, right? Average age, average time. But what happens if the thing you care about is a percentage or a rate? Well, let's jump into our fourth section, Beyond Averages, where we'll compare proportions. And the best part? The core logic is exactly the same.
Let's look at a new case. Imagine an accounting firm wants to know if there's a quality difference between two of their offices. They're not looking at an average score. They're looking at the proportion, the percentage, of tax returns from each office that have an error.
So they take a random sample of tax returns from each office, and here's what they find. In the sample from Office 1, there's a 14% error rate. But in the sample from Office 2, it's down at 9%. Now that looks like a real difference, right? But you know the drill by now. We have to ask, is that a genuine gap in quality or just random noise from the specific files we happen to look at?
Our investigation starts right here with this 5% difference. That's our initial estimate. And just like we did before with ages and times, we can now take this number, build a confidence interval around it, and run a test to see if this 5% gap is truly meaningful.
Okay, this brings us to our final section, where we're going to tie this all together. Section 5, Making Confident Comparisons, aka the big takeaway. We've seen how to compare means, how to compare proportions, but what's the big picture here?
Is that this exact same logic is the engine behind so much of our world. It's how websites do A/B testing to see which button color gets you to click. It's how clinical trials get new medicines approved. It's used to evaluate your teaching methods, to analyze political polls, to break down business performance. It's a fundamental framework for learning from data.
So, if you only remember one thing from all this, let it be this. Statistical inference isn't some magic crystal ball that gives you a perfect answer. It's not about certainty. It's about having a logical, repeatable framework for making the best, smartest decisions you can when all you have to work with is incomplete, imperfect data. It is a powerful tool for navigating uncertainty.
And that really leads me to a final question for you. Now that you've got this framework in your toolkit, think about it. What two groups in your work, or your life, or even just your own curiosities could you compare to make a smarter, more data-driven decision? The possibilities, as you can probably guess, are absolutely endless. Thanks for watching.